Hello. Okay, it's on. Okay, welcome everyone. This is the student research competition session at SIGCOMM'. Today we will have 7 presentations, 1 undergraduate student and 6 graduate students. Yeah, we have a strict time limit, so we will be super sharp. For the undergrad student, he will have 5 minutes of presentation, 2 minutes of questions. For the grad students, 7 minutes of presentation and 3 to 5 minutes to Q&A. Yeah, so without any further ado, let me call our undergrad participant, Man-Hin Yong, and to do his presentation. The stage is yours. Do you need a pointer? Which one is it?
So, hello everyone, I'm Man-Hin Yong from the Hong Kong University of Science and Technology. Today I'm going to introduce my work, the dynamic additive complexity for real-time communications. So, in short form, we call DAYS. So, let's begin. So, the adoption of RTC is reshaping our life. So, in the pandemic period, we have absolutely changed our life forever, right? So, we have the real-time communications, and then in the future, we maybe have a metaverse or remote surgery. And so And for the quality of experience, the image quality is very important. But for now, mainly this is bottlenecked by the network conditions. So in the real-time communications, bitrate is a very important parameter. So if the network is poor, we cannot have a good image quality. But actually, there is other ways, besides increasing the bitrate. So we have a discovery in that. So in real-time communications, the resources is not fully utilized. So you can see in the graph here, right after every frame is finished encoding, and before the next frame is arrived, there is a short period that the raw current resources is idling. So we found that the current resources should be also be considered. Currently, so low complexity encoding parameters are favored to ensure compatibility. And yeah, so for example, in Zoom, so RTC, they usually use a very simple encoding exclusive for superfast or etc. Yeah, but however, using that fast encoding actually satisfies the quality. So our design is to solve the QoT equations outside the network. So first steps is we create a parameter set and ordering them by encoding time. And then we adapt the feedback-driven principle from deep random to control the complexity. So our goal is to have a fine control of different parameters and have a fast response that is achieved by the random. It's a well-known, very fast, and robust algorithm. And it also have a good scalability as this principle can adopt to any encoder. So this is our result. So in relative low bit weights and complex scenarios, we can see that they have a massive increase in the quality, the noise, the sharpness. And in the high bit weight, there is still a relatively significant quality improvement. So this is our data, and see the trend at lower bit rates and more complex video. We have a larger improvement. So our future work on this one is we want to implement into some real-life performance analysis. So we have already tried in RTC. So in the future, we want to try in other applications and also try in other codecs other than x264. And as I mentioned that the control of the encoding parameters is achieved by algorithm and the condition control. So other algorithms can also help the performance. Yeah. So thank you very much. So, and is there any questions?
Okay. Yeah. Thanks. Thanks. Nice presentation. It's time for the questions. We have like 2 minutes for questions.
Hi, thanks for the talk. Do you have an idea what kind of network environments your approach would work especially well for?
So as I show in the site, as I show in the chart, so actually it's going to perform better in a low bit rate environment, and for the latency, so it will introduce a slightly latency. So in the future we need to investigate whether it's like in which scenarios is it worth to switch on the algorithm or not.
Thanks.
Any other questions? There's another question here in the first row, right side.
Can you elaborate a little bit further on the future work regarding the real-world evaluation? How do you want to do this?
So for the future works, we have few plans. So the first one is we want to find out which scenarios we work best, and then to adjust our encoding time target. So for example, adopting some from machine learning to analyze the scenes, and then to figure out how many time we should put in the frame.
Okay, thanks.
Okay, thank you. Okay, thank again the speaker. Our next speaker is, just a sec. It's Katrin Elmenhorst. Now we are going to the graduate category. Please come to the stage. Yeah, there is a pointer if you need it.
No, is there a timer?
Okay.
Oh, yeah. Okay, hi, I'm Katrin Elmenhorst. I'm from Osnabrück University, and I am here to tell you about my poster on BBR performance in virtualized environments. I want to start by saying thank you to everyone who stopped by my poster in the last 2 days. Your feedback was very valuable and very much appreciated. When I thought about submitting a poster proposal to SIGCOMM' about my TCP measurements, I originally thought that I would be presenting something very different than what I am presenting now. And this is because I accidentally ran into a curious edge case that turned out to be more than that. Okay, my TCP measurement setup consists of a rather traditional setup with 2 hosts and a network emulator, but I used virtual machines on the host to, for my original research question, switch around kernel versions more easily. Now, this accidental edge case that I talked about in the beginning that kind of started this work was an unusual and likely faulty behavior of the VirtualBox hypervisor, which meant that the virtual core running the TCP measurement did not get enough host CPU time for the TCP performance to function properly in BBR. And that led to an alarmingly low throughput of TCP BBR in this virtual machine, while at the same time, Cubic was still fine. So this initial accidental finding, along with a paper from Ha et al. In 2021, led to the hypothesis of that BBR reacts heavily to suboptimal scheduling and more than Cubic does. And to test this indicated hypothesis, I applied deadline scheduling to a Chemo KVM virtual machine, which worked perfectly fine in the initial tests. And I basically gave this VM less and less CPU time on the host. And as you can see here, starting at 8% CPU time, BBR performance again breaks down while Cubic is still achieving the available bandwidth. And this kind of shows this correlation I talked about earlier between scheduling and BBR performance. Yeah, so this showed that deadline scheduling can also break BBR. Now the question is why? And for that, I looked into the BBR state machine by reading out socket statistics on a custom TCP server. And I saw that the delivery rate, so how fast am I getting the acknowledgements for the packets that I sent out, was not increasing as fast as BBR was expecting it to, given the initial pacing rate and the first RTT measurements. And since the stalling delivery rate is an exit condition for slow start in BBR, this led to almost all cases immediately where BBR was immediately leaving slow start due to this scheduling problems. Let's stay here. So the question is, why do we have this stalling delivery rate? And my strong assumption, given the evaluated data, is that paced traffic is more affected by off-CPU times than not paced traffic. This is because pacing essentially spreads out all the packets on the RTT, so it requires the TCP process to have the CPU more frequently. But in order to test this pacing idea, another good idea I got from some colleagues was to look at other congestion control algorithms that also use pacing to see if that works. And that kind of brings me to the limitations and future work, because I do want to extend this work in order to look at other traffic that is paced, and also kind of more clearly pinpoint and identify the scheduling conditions that lead to this BBR performance breakdown. And of course, it's also interesting to look at the impact of this phenomenon in the wild. So I need to think about some clever measurement design to correlate host scheduling behavior, which you usually don't have access to, and then the in-guest TCP BBR performance. Okay, so to conclude, I showed a correlation between BBR's throughput performance degradation in virtual machines when a certain suboptimal scheduling was at place. And first, this was observed as some kind of edge case with a likely to be faulty VirtualBox hypervisor, at least in this configuration. But I then showed with further tests that suboptimal scheduling conditions, in this case deadline scheduling, could also break down BBR in contrast to Cubic. And this can be a problem thinking about contexts like cloud networking and CPU contention there. Okay. So thank you for your attention, and if you have any questions, feel free.
Thank you. Okay, it's again time for questions. In the middle.
Yeah, thank you for the nice talk. Do you think BBR version 2 will solve the problem to some extent?
I actually observed this with all BBR versions, so 1 to 3. Although BBR 2 and 3 are only available in Google custom kernels, so there's a little bit of a limitation because you cannot use the same kernel to compare them. But I saw it in all BBR versions, and as I said, I think the underlying cause is the pacing, which is, of course, part of all BBR versions. So it's probably not version specific.
Okay, so a question here about the related work. You mentioned this paper, ICDCS paper from 2021. So did they consider the kind of similar cases when VM scheduling affects congestion control?
Yes, they did. They had a bit more of a theoretical approach to this problem, and what they essentially argued is that during the probe bandwidth phase of BBR, so while it is already going, that the BBR performance can go down pretty heavily due to VM scheduling as well. And kind of my contrast is that I am showing this on a real system, and I'm also showing that it already affects slow start. So it's not even like achieving any anywhere near the available bandwidth, and it immediately exits slow start. So this is kind of, I guess, the differentiation. But they also showed this in a more theoretical way, the impact of VM scheduling on BBR.
And also, 3 years ago, at another European SIGCOMM' in Amsterdam, Venkatarun had a paper, Starvation and Congestion Control, and congestion control. It wasn't in the context of a virtual machine, but basically showing how kind of delays in the end host can undermine congestion control and cause the sender transmit at smaller rate. Just I'm wondering whether you're familiar with that work as well.
I don't think so.
Okay, maybe you should look it up. So again,
Yeah.
I think it was also more on theoretical part, unlike your work, but it's definitely related.
Yeah, I think the interesting part about the virtualization thing is that the whole packet processing is dependent on the host CPU, so that kind of makes the situation worse than it could be in bare metal situations.
Thank you.
Any other questions? Yeah, there is one in the middle. No, okay, my bad. Okay, in that case, time to thank the speaker again. And welcome our next speaker, Louis Navarre.
Okay, perfect. Thank you. So this work is about multicast. All of you know that multicast is efficient to deliver the same data to a lot of receivers simultaneously. And this kind of content is required more and more today in the internet. Actually, Jay Collin, who is an engineer at Akamai, made a presentation a few years ago showing that in Akamai's network, between 20 to 50% of the traffic could benefit from multicast. And here we're talking about a lot of traffic. Like, they reached, and it was multiple years ago, at peak times more than 167 terabit per second of traffic. So multicast was trendy 30 years ago, and with a lot of use cases, like SIGCOMM and the IETF used to use multicast for their conferences. And then the internet became commercial. And so multicast stopped working for multiple reasons. Among them, we have issues when we are doing inter-domain multicast. And because of this, what do you do as an application implementer when you have receivers with multicast and receivers without multicast? And so the solution that we found at that time was using content delivery networks. So just in a nutshell, how I see content delivery networks is that the source sends data to a CDN network, and then some magic happens here, and then the data arrives at the edge. And then the edge uses unicast to deliver the data to all the receivers inside, for example, here, an ISP. And this thing works pretty great. It worked for many years, until it doesn't. So less than a year ago, there was this big fight between Mike Tyson and a YouTuber called Logan Paul. And Netflix wanted to broadcast this, and they made a lot of advertisements. And then it was a complete disaster. Like, a lot of people had stall events. They had also like drops in quality. So it shows that maybe CDN is not always enough as a solution. So remember, I said that we had problems with inter-domain multicast. Indeed, in fact, we have a solution. It's not my work. It's a work from the IETF. And it's called automatic multicast tunneling. So I won't explain it a lot, but basically it enables you to connect multicast islands where you have in the middle a unicast-only network. So it can solve this inter-domain multicast problem by allowing, let's say, incremental deployment of inter-domain multicast. So now, my work, we wanted to dig a bit into the transport layer aspect of multicast protocols. So we started with QUIC. For those of you who don't know QUIC, it's a modern transport protocol with a lot of interesting features, such as embedded security or stream multiplexing, and it runs atop UDP, so it's a good candidate for multicast. In Europe, at least, it's already serving most of HTTP requests, so it means that it's already a deployed protocol, so we can really rely on this for our work. So, as I said, we can use QUIC, so imagine that the client establishes a connection with the server, and then we use something else called multipass QUIC. And with multipass, you can create another pass within the same connection. So the main use case would be, for example, if you are on your phone and you are connected to the Wi-Fi, you create a new pass on the cellular so that when you move away from home, you won't get the failover problem, and so you will keep your connection up. But here we wanted to know, what can we do if we use a separate key for this new blue pass that we just created? And the answer is that with this new key, we can just use the blue pass to transfer data to multiple receivers at the same time. And on top of this, why can't we use IP multicast addresses to send the data on this pass? And if we do this, we can transfer the packets towards multiple receivers at the same time. And so basically it's the object of this work, FlexiCast QUIC. The idea is that we expose a per receiver bidirectional unicast pass and a shared unidirectional multicast flow to send the data to the receivers. And with this, we solve a lot of problems that we had before, like, this one, the receiver on top, it is not in a multicast-capable network. It's okay, it will just receive the data through unicast. Okay, it's not perfect, but at least for the application implementer, it's okay because it's in the same protocol, so it's much easier. Also, if for some reason we have transient failures in the multicast network, or we see losses, we could retransmit them on unicast, or we could switch to unicast for some time. And this is possible because we are using multipass QUIC underneath. So the objective of this demo here at SIGCOMM' was to use FlexiCast QUIC with AMT to propose flexible, reliable, and secure multicast on the internet. So for this, we implemented two use cases. One is a file transfer delivery to show that we can do reliable multicast across the internet, and the other one was a video stream of the Big Buck Bunny movie, because it's a free one to use. And this one just to be funny, but we show that we can almost do it in the browser, but basically it's just a proxy. But the idea was to show that multicast is possible on the internet today. And we also made some experiments on a Wi-Fi setup, because this is also a problem that is really known in the multicast community, it's that multicast Wi-Fi is considered difficult. So just before concluding, during the demo sessions, I had this question multiple times. What is the main economic challenge with this work? And for me, it seemed quite obvious. People are afraid of multicast right now, and so the objective is to get people being interested in doing multicast with us. So I hope that during the demo, everyone who came by saw that it was possible to do multicast, at least to start working on multicast. And what we want to do now is to evaluate the limits of the protocol. And for this, the implementation is open source. We have Docker images of the receivers. You can even host your own server with your own application if you want. So don't hesitate to do this. And just to conclude, multicast worked 30 years ago, but I'm younger than that, so I didn't get a chance to see this. So please make it happen so that I can test it myself. Thank you.
Thanks. Okay. Wow. Okay, time for questions. There is one question here.
Well, I'll go ahead and ask it. Two questions. One, what about congestion control? That's been the bugaboo of multicast for a long time. And the second question, I'll just ask them both. It's never worked multi-domain. Did you run this over multiple domains, multiple ASs?
Oh, sorry, I did. Okay. So for the first question, in this work, what we did was to rely on existing unicast congestion control. So what we do is that because the receiver sends acknowledgement back to the source, we kind of aggregate them, and then, for example, if the first receivers receives packet number 0 until 10, and the second one 0 until 9, we'll say that that all receivers receive packets between 0 and 9. And so, like this, we can rely on existing unicast condition control algorithms. It's not ideal. We have a master student who worked on this, like exposing multiple multicast flow at the same time at different bit rates, for example, for video applications. And then you could use like reinforcement algorithms to determine in which flow you should be based on metrics like losses or delay. So he's here, actually, he's just there. So if you want to raise your hand, Anthony? Yeah, so he's just here if you want to speak with him. Yes, he worked on this. But right now, I didn't spend much time working on this. I just rely on existing work, and so I can have, let's say, a conservative condition control, which is not optimal, of course, but a lot of work has to be done here. Then for the multiple ASs, right now for this, so during the demo, I had my server running in Belgium, and then I had my laptop here in Coimbra, and so for this we use AMT to connect the multiple domains. So right now, not a lot of ASs are hosting AMT relay and gateway to do this. Lenny Giuliano, who is working at Juniper, is pushing this work called 3DN to do this in the Géant network, if you want to have more information about it. So you have to host your own AMT node to do this. So that's also part of what I want to do here, is to gather people into doing this themselves. Thank you.
Other questions? There's one in the middle.
Well, there are many explanations why IP multicast didn't take off. So I think my personal kind of view that economics were not right, because if you look at the transit provider, you do extra work, you create, I don't know, multiple copies of the same incoming packet in various routers and switches, but you get paid only for one copy, unlike with unicast. Right? So do you have any thoughts about economics of it, especially when you go beyond the tunneling to reach remote domains, but work natively end-to-end over multiple domains?
So there are maybe multiple ways to answer this question. The first one is that with AMT, because you are tunneling the data, you could get some information here, so you can get insight on how many, at least, duplication you are doing, and if it's just a duplicating a single packet for another domain, maybe it's not that much of a work, I don't know. The other way is that because here, compared to older multicast transport protocol, here we exactly know the set of receivers that we have. So here, because we know the set of receivers, we know the number of copies we are doing from the source toward the receivers. So maybe we can have some insight from this. So it's just the starting point. To be honest, my advisor sent a week ago like 10 emails in 30 minutes to a lot of ISPs network to like share ideas on how to do this. But I think that with AMT and the fact that we exactly know the set of receivers at the source, we could do something. So we have to think about it. Here is just a starting point. Of course, it cannot be deployed tomorrow on the internet. But I think there are a lot of ongoing effort that could be done to do this. But at least we have the tools to do it.
Thank you.
Thank you.
Okay, I guess it's time to thank the speaker again.
Thank you.
And welcome our next speaker on stage, Yiming Lei.
Hello. Hi. Thank you very much. I'm Yiming from Max Planck Institute for Informatics. Today I will talk about time synchronization for reconfigurable data center networks. Reconfigurable DCN use optical switches to build a network. Optical switch is more energy and cost efficient than traditional electrical switches. And here is a common architecture of how RDCN is structured. So people use OCS, optical switch, to connect electrical endpoints. They could be top-of-rack switches or hosts through direct links. And this OCS can build different inner connections between ports and change this topology change this topology over time based on a preloaded topology schedule. Recent research on RDCNs targets on microseconds or even nanoseconds topology changing interval to provide connectivity during a short period of time. However, time synchronization for RDCN is still understudied. It is important because routing on RDCN depends on accurate clock. Even though these electrical nodes can know the topology schedule in advance, they need to have the synchronized clock to know what topology it has at this moment. And this system needs a guard band to let the electrical nodes know how long in advance to stop sending packets to avoid packet loss due to the topology changing. So the error bound is an essential metric needed by time synchronization in RDCN. This is also a challenge for the time synchronization on static DCN. Current protocols usually use a spanning tree algorithm to propagate a clock from the reference to all other nodes. However, dynamic topologies in RDCN disrupt this clock propagation tree. Nodes has no way to know who to synchronize with. So the question we ask is it possible to build a general time synchronization protocol for RDCNs that doesn't depend on specific architecture or specialized hardware? And what's the synchronization accuracy we can achieve? The key question is who should a node synchronize with? We start this by analyzing where the synchronization error comes from. The first factor is clock drift, caused by the frequency difference between different clocks. After synchronization, the clock value will drift to each other. And the second factor is hop error, which is caused by a small noise of the synchronization operation itself. And this absolute synchronization error cannot be known during the synchronization, but its maximum value, which is also the error bound, can be known and can be tracked by each node. Based on this insight, we design error-aware synchronization for RDCN, where nodes keep track of their error bounds during the whole process and only synchronize with the node which can reduce its error bound. In this example, node J will only synchronize node I if node I's error bound is bigger than node J's error bound plus the hop error bound, which is caused by the synchronization operation. Let's see an example. So the node 0 here is the reference clock, which always have an error bound of 0, and all other nodes has an initialized error bound of infinity. And at this point, node 0 will synchronize node 1 and 7 because this can reduce its error bound to 5, which is the hop error bound. And as time goes, the error bound of clocks grow because of the effect of clock drift. And at this point, node 1 can synchronize node 3 because it can reduce its error bound. And for the same reason, node 0 synchronize node 5 and 6. And all nodes follow these rules across the whole duration to minimize their error bound. And this is an example implementation of our protocol on the Ethernet. And the synchronization message will contain the current clock value, which is a timestamp, and also the current clock error bound. Each node will broadcast the sync messages to all of its neighbors, and the node will only update the clock if the received message has a lower error bound. And we evaluate our solution on a large-scale simulation with 128 TORs and 8 upper links per TOR. As the first work of this kind, we compare our solution with baselines running on static DCNs just to put the numbers on context. First of all, our solution can achieve sub-10 nanoseconds sync interval of sub-10 nanoseconds maximum sync error. And compared with other solutions, surprisingly, we outperform solutions on static DCNs. And this is because we use the metric error bound to get the synchronization process so that nodes can synchronize with a clock with better quality. And also, we leverage the dynamic topology on RDCNs. Nodes can be connected with different nodes during a period of time. And yes, we can build a general time synchronization for RDCNs, and we can achieve sub-10 nanoseconds maximum synchronization error and enable microseconds time size duration of RDCN. To conclude, time synchronization on RDCN is essential and challenging. It has a unique requirements of error bound. And we design our error-aware clock propagation to outperform solutions on static DCNs. And last not least, time sync is just part of open optics, an open research framework we proposed, open research framework we built for easy design, testing, and deployment of RDCN for everyone. You can implement your design in 10 lines of Python code, and we have open source our code and the tutorial material we hosted on Monday. Feel free to try it out and follow updates. Thank you very much.
Thanks. Yeah, it's time for Q&A. Any questions? No one? Okay, no questions. That's that's a surprising. I was wondering, in that case, I realized, do you have any, are you planning to try this with a real implementation or just in?
I see. So we have an implementation on the testbed based on Tofino switches, but our method is pretty general. It just needs to have a packet header of containing timestamp and the error bound, which is pretty similar to the current PTP implementation. And for the evaluation I show here, we did large-scale simulation that contains all factors that cause synchronization error, which is drift and hop error.
Okay, thank you. Any other questions? Okay, another one from me then. Do you know any other related work that has a similar goal, and how does your solution compare to them?
I see. Thank you very much. So there are many work on RDCN, and so they either assume to use the specialized hardware, or they propose to use out-of-band management network. And the key point of this figure is shows that even if you have a static management network to do the time synchronization, to synchronize on the optical domain can still achieve better synchronization error.
Okay, thank you. Yeah, question there. In the middle, in the front. Okay.
You mentioned about OCS in the beginning, right?
Yeah.
But your timing information is in the packet. Does that mean OCS need to recover the packet?
Thank you very much for the question. So OCS is a passive switch. It just builds direct connections, just like fibers between different ports. OCS is not aware of what's happening in the packet level. It doesn't need to recover the packets, and the electrical nodes will just send out sync messages whenever there's a connection.
So the reconfiguration of OCS, how does it happen?
I see.
Do it through a management layer, or?
Yeah. Yes, it's through the management. It's through the management plane, and OCS usually has a controller that controls the connections it provides for different time.
But you won't have a nanosecond accuracy then, right? Am I correct? I mean.
Yeah. So the OCS controller is usually a server or FPGA directly connected to the OCS. So for this kind of OCS, it's designed to be synchronized with nanosecond level. And our solution can synchronize with the controller to, yeah.
Okay.
For an optical switching network like this, how fast or how accurate does the time synchronization need to be? Which I guess another way to put that would be, if you have the improvement in accuracy that you have, how much does that ultimately benefit performance of the overall network?
That's a great question. So regarding how accurate we need, the more frequent the topology can change, the full connectivity can be provided during a shorter period of time. So we want as quick as possible. Basically, our solution can achieve sub-10 nanoseconds synchronization error, which means we can set the guard band of system as 10 nanoseconds. If we tolerate 1% of overhead, we can support 1 microsecond slash duration when topology doesn't change.
Okay, so I guess it's time to thank the speaker again.
Thank you very much.
And welcome on stage, Saeed Khalai.
All right. Hello, everyone. This is Saeed, and I'm going to talk about the storms above, disruptions below poster, to map the impact of extreme solar storms across orbital regimes. To be starting with, our Earth, our favorite Earth, has a geomagnetic field that protects us from any particles coming from the space. But when we have a solar storm, we are talking about a large flux of high-energy particles flying towards the Earth. But what happens is when this collision happens, when these particles reach into the higher atmosphere, the event is we will experience two types of event. First one is this collision will target the neutral atoms and molecules in the higher atmosphere, which we call it the thermosphere. This collision caused to knock off all the electrons in those molecules and atoms. That results into ionization. And the other one, which is the instantaneous increase in the temperature and the heat in the thermosphere, basically causes the thermosphere to expand toward the higher latitudes. And we know what is solar storm now, but why it concerns LEO satellites. In terms of the thermosphere expansion to the higher latitudes, we are talking about creating a more denser molecule and gas around the higher latitudes in the Earth, which for the connectivity, it can cause, there is a good chance to cause more connection dropouts and experience high latency, packet loss, and degradation in the throughput. But the question is it gonna be the same for all the locations on the Earth? According to our findings, it's not. And the higher latitudes are more vulnerable to the solar storms compared to the lower latitudes and mid one near the equator. But crossing the horror part of the story, what is our contribution? According to the space weather data and also the NOAA KP index that we could have collected with a high accuracy, basically 24 hours before solar storms, and the testbed opportunity that we have, which is active across different latitudes over the years from up to Canada down to Antarctica, we could have run fine granular experiments in the testbed in different locations, which you can see that we have tested UK, Germany, Canada, and Nigeria as our examples to see the effect of solar storm. So according to the unique data set versus the quiet days baseline, we saw that the countries in the higher latitudes to mid ones, like UK and Germany and Europe and Canada, they are experiencing even 20% of degradation in throughput and 10% in RTT. But for Nigeria, the effect can be even ignorable. The thing is about Nigeria, the maximum amount of changes during the solar storms are up to 5% in center of Africa, almost, we can say. And this one is another evaluation that we have gone through in Oslo, Norway. We've seen that during the solar storm, as the extreme storm during the October, we've seen the RTT is roughly jumping from 60 milliseconds to 72 milliseconds during the storm. And one of the interesting observations that we had was losing the connectivity between the dish and the satellite, which in the same quiet days, and considering removing the weather impact as another environmental impact and normalization, we've seen that the connection reliability between the dish and the satellite has decreased from 99.5% to 98% during the solar storms. But since we had the testbed and we had the data, basically we constantly run a space weather data collection to collect all the information about the aurora ring around the Earth. And we have fine granular, like every 1 minute and to every second, active controlled measurements according to the storms, and the gRPC telemetry data collection, and also the TLE of the satellites from Celestrock. We came up with a random forest classification model to predict the anomaly over the LEO satellite networks by 24 hours ahead. So if you feed the model with the coordination, and by coordination I mean longitude and the latitude of your node, you will have the probability of the degradation you will experience in terms of throughput, I mean uplink and downlink, packet loss, and the RTT you will experience in your Starlink connection. And I want to use this chance to thank you all, the ones who stopped by, and the SIGCOMM for the opportunity, and I'd love to answer your questions.
Thank you. So time for questions. Yeah, here is one.
Thank you. On your last slide, you had the item on anomaly detection. Which type of anomalies do you consider?
Basically, our mean by anomaly is considering only solar storm at this stage. And the anomaly, we are considering the degradation in the performance. And the metrics, as mentioned, are actually the uplink and downlink throughput. And it will tell you, for example, if you want to see the throughput that you will lose in the next 24 hours according to the solar storm, it will give you the probability and the exact percentage of the throughput you are going to lose. Or same for the RTT and the packet loss that you are going to experience.
So I think there has been a long line of research on solar storms and impact on satellites even before Starlink. And apparently there were cases where satellites were actually knocked down, not only throughput goes down. Yeah. So you do want to comment on this, and also maybe to comment on whether it's, you work about measurements, but do you have any kind of implication and advice on actually operation of satellite networks, given the impact you observed?
According to the related work that you mentioned, and thank you for the question, in 2022, Starlink lost 38 satellites due to the extreme solar storm. So basically, we are talking about billions of dollars in terms of the money. But for the mitigation, right now, our research has gone through the 24 hours ahead information and the prediction. But the thing is, regarding the satellite maneuver and the drags that we have measured during the solar storms, if Starlink knows that the solar storm affects 24 hours, they can do the maneuver at least to save the satellites that are in danger, and they have like higher technology and would be more like we can say more cost effective. And in terms of the related work, other related, so yeah, we've seen like 3 workshop papers, 2 at this SIGCOMM, talking about the solar geomagnetic storms and different aspects. And the difference I can say that we have is since we have the latitudes, different latitude access, and the granularity of our measurements 1 second, which what I've been seeing in those measurements is like we've seen 4 minutes interval of the measurements, and our experiments have been totally customized by ourselves, and they are coming from the space weather, according to the space weather data, minute and hour exactly.
Thank you.
Yeah, there is a question there. Yeah.
Thanks for the talk. So you mentioned that potentially Starlink could use this kind of measurement information to prepare their satellites to reduce the probability of failure. Are there ways that with this real-time measurement you could use it to improve performance of the network during a storm?
Thank you for the question. In terms of the satellite itself, there can be like future work, as said, to do the maneuver. But in terms of the networking, if we have the specific protocols, so the future work would be the specific protocols for LEO satellite networks. So basically, an example would be a congestion control, right? A mechanism, or even any other protocols to be tested in this LEO environment, which we have like some part of it is like a black box. But other mitigations that we can like have during the solar storms would be controlling, for example, in the same congestion control, controlling the pacing rates. And it's just an example to avoid the throughput degradation, or even prioritizing the traffic or classification of the traffic during the solar storms. And other thing is the user end measurements to be continued with for the networking.
Okay, I have one final question. Yeah, here on the stage. Or anyone else? No. Okay, so my question is, which links are more affected by solar storm? Satellite to satellite or satellite to Earth?
If I understand your question, you mentioned which satellites are under impact or something, because I don't see you, sorry.
Yeah, no, I'm here on the stage, but by the
sorry.
way, hi, nice to meet you. Yeah, I mean, you mentioned link failures, and you mentioned there is a percentage drop, and do you have any insights on whether these are satellite to satellite links or satellite to Earth links?
Basically, with what we have collected in our data set, we have collected the different technologies of the satellites and the impact on the even granular to the launch groups, different inclinations, and even going through to MEO satellites and GEO satellites during the solar storm. And we've seen the LEO satellites are more vulnerable, and according to the inclination and the orbit, we are talking about more than 90 degrees, more satellites are in fact. But the one thing that is really important is the satellite would be above the location that is facing the sun.
Okay,
would be more vulnerable.
Okay, thank you. Thank the speaker again. And welcome our next speaker, Farbod Shahinfar.
Hello everyone, I'm Farbod from Polytechnic of Milan. It's my honor to have the opportunity to present my work about cache efficiency in eBPF programs. So I don't know how many of you know about eBPF. eBPF is a new technology, a set of tools that allow you to run some small or maybe big programs inside the operating system, Linux kernel mainly, to customize it, to add new functionalities. It has reached many applications, including network functions, and people are using it for implementing firewalls, load balancers, doing telemetry. The thing is, eBPF is running inside the operating system, inside the kernel, So it has a very restricted environment, very restricted set of rules that it needs to adhere to. It needs to go through a verification phase. It has a very limited APIs for managing memory and state. So given that, and given the type of applications that eBPF are, applications that are using eBPF, for example, firewall, they are stateful. They are managing large tables mainly. What we observed is that when the size of the table increases, the throughput starts to decrease based on the number of entries inside the tables. And it's mainly because with the larger number of entries in the tables, the probability of having the data that you want in the CPU caches decreases, and your program basically experiences cache misses, which causes memory stall. This is something very common. It happens to any type of software. But as an eBPF program, you cannot do much. You just realize the fact that your application is experiencing cache miss, and that's all you can do at the moment. In this work, we try to figure out when eBPF was designed, what set of options, what design choices was neglected that caused this situation that eBPF programmers cannot actually try to optimize their programs for cache efficiency. We find three challenges very important. One is that eBPF programs do not have a very rich API for describing their own data structures and managing the way they want the memory layout of their applications. They don't have access to the prefetch instruction. Prefetch instruction is now available on all modern CPUs, allows you to asynchronously load the memory addresses that you want while you're doing some calculations processing. It's very useful for these scenarios. And the other thing is that eBPF programs were designed to receive an event, a packet, and run to completion, which causes issues. In this presentation, I focus more on the last one. So let's assume you have a packet processing eBPF program. You receive 2 packets. Your eBPF program receives the first packet, starts processing. At some point, you can see here on the figure the yellow one and the green one, 2 packets. At some point, your program experiences a cache miss. It needs to wait until the data is loaded into the cache and available for processing, and this causes some bubbles in the execution, so your CPU is not being utilized fully. It would be so, as I said, it's because eBPF is doing a run to completion processing of packet, but it would be really nice if we could somehow achieve the second, the bottom part of the figure, which means when the first packet is experiencing the cache miss, it would be nice to start doing processing an independent event like another packet and actually utilize the CPU and save time. So we thought, okay, how we can enable eBPF programs to do this. And if you remember, the reason we couldn't overlap packets was because of the assumption that eBPF receives 1 packet and does it run to completion. So we could either change the first part of the assumption, receiving 1 packet. So if you receive a batch of packets, then the programmer could write a code that starts parsing the first packet, prefetches the memory it wants, then meanwhile switch to processing the second packet, and hopefully by the time it has processed the second packet, the data will be in cache for the first packet and then switch back to the first packet. This could work in theory. It needs to change the API of eBPF. It's harder to write the batching programs. And when you have a batch of packets, basically your batch needs to go through same type of processing. So if you have a packets for very different type of, so for example, if your firewall have multiple different paths of processing, then the batching starts to break and it becomes less effective. Another approach to break this assumption of run to completion is to receive 1 packet but don't run to completion, Instead, start processing your packet maybe halfway through, but break your program into stages. Process your packet. At some point in your program, you realize that, oh, I want to do prefetching. You do prefetching, but you don't want to continue, so you notify the eBPF runtime that at this point I want to yield the CPU, and you let the runtime decide if there is another packet to process and start a new processing. This way, you effectively break the assumption, and you can again do the overlapping and achieve, you use the time bubbles and achieve better utilization. Of course, it won't be without overheads. Doing this will add cost of doing the context switching. In this work, we prototyped this idea with some other optimizations inside the user space eBPF environment. And as you can see, yes, doing this type of context switching does add overhead when we have very small tables, very small number of entries to access, and there are not much cache misses. Doing this context switch does add overhead, around 17%. But when there is cache miss happening, it is really effective in hiding the memory access latency and can improve the performance. So the takeaway is that eBPF programs do experience cache misses, and with the better support from the eBPF runtime, we can actually do better and hide the memory access latency. Thank you. Thank you very much.
Thank you. Again, it's time for the Q&A.
Thank you. Very cool. You showed on your previous slide one flow and 7 million flows. One on the left side, baseline is better, on the right side the other. Where is the crossover point? Did you experiment in the middle?
Good question. Good question. For this specific test setup, no, I don't have the figure to show to you. Yes, but I can tell you that. So this one is the user space environment that we were testing. But if you look at this other figure,
yeah, okay,
which is from the actual eBPF runtime inside the kernel, when you have around thousands, tens of thousands of entries in your table, it becomes really obvious that you have cache miss issues.
Okay, thank you.
So my question is about this software prefetching.
Yes.
As do you know, I suppose it's an Intel architecture, no? Is an Intel architecture have this hardware prefetcher that do a lot of works. There are many workloads in which if you try to do software, you lose performance because.
True.
So do you know which is, in this case, the effect of the hardware prefetching? Did you try to, I don't know, disable or modify the configuration of the hardware prefetcher? Or?
Okay, true, you're right. So, yes, in our prototype, we add the prefetch instruction to eBPF programs, and what you see is that if you do the prefetching at the wrong moment, for wrong things, you start to interfere with the hardware prefetcher, and the performance actually get impacted and get decreased. So it's actually, yes, it is a bit, it requires a lot of measurement to know exactly what type of your program is experiencing cache misses, and where you should start doing prefetching to get the performance. Yes, that's true. Sorry, did I answer the question? I think I forgot one part of the question.
No, more or less. Do you think that, I don't know, disabling the hardware prefetcher can further increase, or there is an let's say, interaction between the software and the hardware? You saw this.
There is an interaction. I haven't disabled the hardware interaction, the hardware prefetcher to see how it changes, but I can say yes, there is an interaction, and if you start doing the prefetching, you should keep in mind that you might interfere with the hardware. So I see that for random memory access, like when you have a hash map and things like that, the manual prefetching does better But for arrays that you are accessing sequentially, the hardware prefetcher does much better. Yes.
Thank you.
Thank you.
Yeah, that's a follow-up question to yours question regarding the evaluation. I mean, can you relate the numbers to real-world scenarios? So what does it mean, 100 flows, 7 million flows?
Okay, yes. I realize that the flows is a bit confusing here. So this experiment is a eBPF program having a hash map with certain type of rules and counters for different type of flows. So we generate a certain amount of traffic, I guess around 10 million packets per second. But we vary the type of the traffic, which means the number of 5 tuples of packets we have. So in the 100, for example, when we have 100 flows, we are uniformly selecting 100 different 5 tuples and generating traffic at 10 million packets per second. When we have 50,000 flows in this figure, we are selecting from 50,000 different 5 tuples and generating traffic toward the eBPF program to see how it affects the memory access. Thanks.
Thank you for your talk. So I have a question. Intuitively, this will definitely increase throughput. Have you tried to measure the effects on potential latency predictability as you start batching packets and interleaving processing instead of running to completion?
Sorry, what was the question?
Have you considered effects on latency predictability once you start batching and interleaving rather than running to completion?
Yes, you're right. So one thing that happens with batching, especially if your program has multiple different paths, is that you should wait for all of the packets in the batch to finish. So if for example, half of your batch is for type A packet processing and the other half is for type B packet processing, then you'd go through the type A and then you should wait for type B to finish too, so that you release all of the batch. Yes, this could cause unpredictable latency for packet, because you can imagine receiving a batch of homogeneous packets and unhomogeneous packets. No, I haven't looked deep further into it, but I guess with the second type of with the cooperative execution type of overlapping things, you have a better control over how it's scheduled, and the effects should be less pronounced than having a full batch. That's one benefit of doing it this way. Thanks.
Okay, it's time to thank the speaker again.
Thank you very much.
And welcome our last speaker today on stage, Yannis Protageras.
Okay. Hello, everybody. My name is Yannis. I'm a first-year PhD student, and I'm here to talk about our ongoing research on benchmarking LLM systems on networking operations. So you probably all know that there is a lot of excitement about using LLMs in just about anything, and managing networks is, of course, no exception. However, we need benchmarks so we can concretely answer the question of whether they are actually any good at this. Network management is an error-prone and critical task, after all, and human errors still continue to cause misconfiguration that are associated with major costs. So before we even consider involving LLMs in the process, we should deeply understand what hinders the reliability. So I'm going to talk about some of the challenges that come with designing such a benchmark. First of all, in a good benchmark, we need complex and realistic tasks, but realizing this is difficult because there are no clear metrics that can define how complex or not a misconfiguration incident is. Added to that, A good benchmark must have tasks that are difficult to solve but easy to verify. So our tasks also need to be well defined. And for that, we need to consider the following, that a fault in the network state does not exist in a vacuum by itself, but it exists in relation to the intent of an operator about the state of the network. So this intent is something that we must encode into the modeling of the problem. So for our benchmark, we use formal verification to both formulate the problem statements and evaluate the proposed solutions. First, for our test generation, we simulate network incidents by injecting faults into network-wide configurations. So we start with a healthy network configuration, and then we end up with a faulty and unhealthy one. Then we use the tool config to spec, which relies on a form of verifier to extract the specification of both the healthy and the unhealthy network. The specification provides basically a description, a projection of each network's forwarding state, forwarding behavior. So we can basically assess the damage that is done in the unhealthy network by comparing the forwarding behavior of the healthy and the unhealthy network. We then use all this data to provide the problem description to an LLM and prompt it to find the misconfiguration in the network-wide configuration and fix it. We then evaluate this reconfiguration by, again, extracting through config to spec the specification of the proposed fix, the reconfigured network, and comparing it with the specification, so the forwarding behavior of the original, the healthy network. If the proposed fix is completely correct, there should be a complete 100% overlap between the specifications. So we performed an initial evaluation for 3 different foundational models in 102 scenarios, and since we used LLMs in a pretty simplistic way, we basically used them by themselves, they performed pretty poorly, even in simple tasks on small networks comprising no more than 20 routers running BGP and OSPF. We believe that this highlights the importance of also working on the system around the LLMs, other than the LLMs themselves. And here I briefly mentioned some of the more specific challenges that we are currently working on, and they include generating realistic and diverse network-wide configurations and misconfigurations to address their general unavailability. And we are trying to extend the types of specifications that we support in our benchmarking pipeline. And we are also trying to effectively handle the exploding context of the network configurations and the specifications and all the artifacts that can describe the network state. So in the end, what we are trying to offer to the research community is a benchmark with a quality that we can vouch for, and a benchmark that anyone can use to test their language models and the systems around them. We also hope that this system facilitates and furthers the analysis on the LLM's limitations and different failure modes. So in the end, ultimately, we can more accurately guide the research for the development and their applications in network management. This is the end of my talk. Thank you very much for your attention.
Thank you. Okay, time for questions. Okay.
Really? Nobody?
Yeah, one question from me. I was wondering, you showed different LLMs and different models, and have you checked?
Yeah.
Yeah, have you checked different model versions as well? Is there any change as they progress? They get newer or better, or you just selected these 3 and had no time to do an in-depth analysis?
Sorry, I can't hear you well enough.
Excuse me?
I can't hear you well enough.
Yeah, my bad. So what I wanted to say that, for example, you mentioned GPT 4.1. Have you tried GPT 5 or GPT 4, and do you see any differences?
Yeah, so these experiments were conducted back in April, which was around where we were working on the implementation for this poster. Right now, we haven't tested the newer models because we are focusing on constructing a benchmark which can be more, expressive. We can achieve more. We can extract more meaningful results. So we can then conduct a more extensive evaluation of more models, because you can understand it's pretty costly to run a benchmark like this on on many different large language models.
Yeah, that makes sense. Yeah, questions are all over the floor. Yeah.
Thank you very much for the great talk. One question is, how can we handle the challenge of when we evaluate and generate a benchmark? A lot of components are involved in the whole system, including the model accuracy and also the evaluation software, pretty much the prompt engineering code, right, to generate the results.
Yeah. I think if I understand correctly your question, we basically want to measure the impact of each specific component that we may implement for a solution in such a system that tries to tackle this problem. And if I understand correctly, then I guess on top of my head, we could use such a framework to possibly perform some sort of an ablation study so we can independently measure the effect of each component of that larger scale system.
Okay, thank you.
Yeah, next to you.
Brief question. I mean, how do you prevent side effects by third parties that may also use the LLM?
Are you talking about side effects in the network state, by proposing a reconfiguration?
Yeah, and I mean, the interaction with a large language model.
Yeah. So it is true that a model can propose a reconfiguration that may fix some original problems that existed in the network, but then introduce a lot of other ones. This is encaptured by the metric that we define in the benchmarking by calculating the overlap between the behavior, the forwarding state in the golden state of the network, and the one in the proposed fix. If there are side effects, they are to be reflected in that score. And it is also very important in the same vein to have some metrics that explicitly capture the safety of each proposed solution.
Yep, with a question in the middle.
Are there other similar LLM benchmarking environments, and how do they compare?
Recently, there have been works proposed on pretty similar objectives in networking. I would say they could all be considered complementary, because each one can let's say, evaluate a different aspect of the LLM's general reasoning capability on specific domain tasks. And on the top of my head, I remember of a benchmark that was also presented in a workshop here that focused on the evaluation of LLM agents in more holistic environments that involved interaction with environments and tool usage. I think that all of those benchmarks can provide different insights, and they are all useful for the community to exist. And it's even more so if they can be easily accessed and used by the community.
Cool, thanks. One other quick question.
Yeah, of course.
Have you gotten any intuition about, are there easier cases and harder cases? I'm trying to understand is 53% good or is it bad, right? Like if you gave these same problems to a human, how many of them would they be able to find and fix?
Now that's a very interesting, a great question. Now, as I mentioned, those tasks were on pretty small scale networks. I mean, they comprised no more than 20 routers. And I guess that for the more simple ones, human operators would be pretty easy, would be able to solve them pretty easily. But still, even if the networks were pretty small, still the interplay between the different protocols that are that exist in the network, and the different parts of the device's configurations that it might still be confusing. But with everything that we hear about the model's capabilities, I mean, people would expect that they would be able to handle tasks like this more easily. Though, but it was apparent that even for such small-scale tasks, because real-world networks are considerably larger than that, and they should be supported in such evaluation frameworks. When they are used by themselves, they perform poorly when compared to what we would expect of their applications to the real world.
Okay, any other questions? Okay, that time's up. So that was the last question and the last presentation. Thank the speaker again.
Thank you very much.
And thank all the speakers again. Nice, great works. Now, I would like to ask the juries to meet in the front row and have a short discussion. Thanks.